Hey everyone, welcome to your Play Posit for the day. We're going to be covering lessons 2.2 actually to 2.4. We're into our second unit of the year. Time's already flying by. I wanted to share with you guys something that you may have seen before, especially if you've had me as a teacher, but something we're going to do in class is share some did you knows. So ways that math is used in the world around us. And one of them, especially geometry, as you can see on this slide, is used in baseball. So math is used obviously in sports statistics, but also you can see the baseball field and all the different areas have to use precise mathematical and geometric calculations, especially the angles at which and see, I'm not a good baseball term person, but angles at which the like first base to second base, this line here, that must have a special name in baseball. But it does have to meet a 90-degree angle, for example, here. And just look at all the degrees, the different sizes to be mathematically accurate and accepted into the MLB. So, excuse me, it's just amazing to see all the math involved and things that maybe you didn't realize. Before we get started on the lesson for today, I wanted to just flash back to something in our previous lesson. And I'm hoping some of you caught this, although I didn't hear from anyone. But as I was reviewing our Play Posit from last week, I realized that I made a mistake. And you know, it happens, everybody's human. But you can see we did the rules for reflection across the x-axis and reflection across the y-axis. But look what happened. I wrote 1, -4 here. See, because that's the point we were working with. I made the y negative. So then we were going to make the x negative, right, to do that y-axis reflection. But when I made the x negative, I forgot to bring along the -4 with me. So let me grab my pencil tool. In reality, this should say -1, -4, which we know is answer C here. So go ahead and go back to your notes and make sure you make that correction. And I appreciate your patience. Next time, if you notice anything, say, hey, Miss Wenzel, that doesn't seem right. Please make sure that you reach out to me. All right, so today we're going to get into inductive and deductive reasoning. I'm going to look at some proofs, kind of looking ahead into what kind of proofs we'll be doing this year. And just a heads up, this unit is different and interesting and really cool, really thought-provoking, something maybe you never realized you would ever do in a math class. So there's a lot less numbers involved, which kind of surprises a lot of people. But I think you guys are going to get a lot out of it, a lot of problem-solving skills. So before we do that, I always like to flash back to previous topics. It just kind of keeps us in the know of all the things we've already covered throughout the year. So here, they give us a bunch of math information and a diagram. Remember, in geometry, you're almost always going to see diagrams. And if you don't, you should probably draw one. So whenever they give me some stuff and a picture, I like to label the picture. So VUT is 175. This whole thing is 175. VUJ, so just this angle here, 17x minus 3. And JUT is 17x plus 8. Find the value of x. So anytime we know the two parts, right, we know this part and this part, all add up to 175. This is the angle addition postulate. We know the two parts added together, this one plus this one, equals the whole thing. And now we get to use our algebra. So we're going to combine like terms, -3 plus 8, and 17x plus 17x. Whoop. All right, so 17 plus 17, what is that? 34? -3 plus 8 is +5. And you can always use your calculators on these too, you guys. We have calculators for the whole class, just like last year. To get x by itself, we're going to move the 5 over by subtracting it. Remember, that's the inverse of addition. 175 minus 5 is 170. And our last step, since this is multiplication, we're going to divide by 34. And when you do 170 divided by 34, you do get 5. So x equals 5. And we're finished. In this case, they just wanted us to find the value of x. Be careful though, because sometimes they're going to want you to find the angle measure, in which case you would just take that x value and plug it back in. Okay, so proofs and logic. Check out this cartoon. I'm going to move my face. Hopefully that doesn't block your viewing of this cartoon. Penguins are black and white. That's true most of the time. Some old TV shows are black and white. Also true. Therefore, based on logic and facts, we're going to say some penguins are old TV shows. And hopefully you're going, what? That doesn't make sense. So sometimes facts and logic can lead to the wrong conclusions. And we're going to look at different ways we can avoid that. And we can do that by finding what are called counterexamples. So these are all things we're going to cover together and what you're learning in your OMHS the next few weeks. This is all based on problem solving. You guys are going to be given some facts, given some information, and we're going to be able to make some conclusions based on the logic laws and rules we learn. So basically, we're studying logic for mathematical problem solving purposes and also just non-mathematical problem solving purposes. Although I would argue all problem solving involves math. We can talk about that another day. There are two types of mathematical logic. Get my face out of the way. Inductive reasoning and deductive reasoning. So we're going to learn about those two types. The first type is inductive. So that's where you take small, specific examples, and then you're able to make a big, grand statement, a big general conjecture. A conjecture is just a statement or a rule or a fact. So by observing small individual things, you start to see a pattern, so you can make a big statement. Here's some examples. I don't know if you guys know who this is, but you observe that Tony has red hair and a short temper. Tommy has red hair and a short temper. Timmy has red hair and a short temper. So you've based all these three observations, and you're going to make a conjecture. Whether it's true for all people or not, you're going to say all people with red hair have short tempers. Or if you have red hair, then you have a short temper. Now, this may or may not be true, but you're making this conjecture based on these observations. We use it a lot in science. Here's another example. I keep thinking you can't see what's on the screen because of my image, my recording. Okay, China's rare river dolphin now extinct. Experts announce. So this is actually from an article. The rare Chinese river dolphin has gone extinct, according to scientists who could not find a single one of these animals during a 6-week search on China's Yangtze River. So they searched for 6 weeks and they could not find a single one. So they took all of those observations, however many times they were searching, maybe they did it all day, they probably did it in shifts, and said, they're not here, there exists. So if an animal is a Chinese river dolphin, then it is extinct. Now we know that there are animals that are extinct because they've not been found anywhere, and scientists observe this and they record this, keep track of it, and then they finally say, okay, this animal is extinct, it doesn't exist anymore. But what if somebody found a Chinese river dolphin one day? There's a special name for that, and we're going to learn more about it later, but that's called a counterexample, an example that counters the statement, that proves it false. Counterexamples are used a lot in debates, so we use math and debating as well. You guys have heard of Sherlock Holmes. He often used inductive reasoning. He would observe that a particular dog would bark at strangers, and that dog would not bark at its owner. So the dog only barked at strangers. From that, he conjectured, or he made a statement, This dog barks at everybody except its owner. So if you are not the owner of the dog, then the dog will bark at you. So Sherlock Holmes made all these specific observations and made a grand statement about this dog. The dog does not look very friendly. Whew. So let's try using inductive reasoning for ourselves. Here's some observations. You observe the number sequence. 1, 1, 2, 3. I know you've done these kinds of observations in the past, but by observing this pattern, what do you guys think comes next? Probably taken some time to think about that and see the pattern, see what's happening. We're adding, so 1 plus 1 gives you the 2, 1 plus 2 gives you the 3, 2 plus 3 gives you the next number would be 5. So based on these specific examples, we can make a conjecture about the number that comes next. We can make a general statement. So we could say the next number in the sequence is the 2 previous added together. This grand statement gives the reader or the user or the person the rule of what comes next. Or like the Sherlock Holmes example, everybody now knows the conjecture or the rule about that dog. But wait, be very, very careful because there can be a problem. Sometimes inductive reasoning can be wrong. You guys remember the example about the red hair and short temper? So we saw these 3 observations about Tony, Tommy, and Timmy. They all had red hair and a short temper. So we said, hey, that must mean all people have red hair and short tempers. From these observations, we could also conclude that all people with the names that start with T have red hair and short tempers because we're seeing patterns, right? So we could say, if your name begins with a T, then you have red hair and short temper. That might be true for these observations, but can you guys think of a counterexample? And I love doing this in class with you too, because somebody will say, well, I don't have red hair and my name is, Thomas. So you can think of a person or find a person whose name starts with T. Maybe, now I can't think of T names. I said Thomas, that would work. Taylor. Taylor has brown hair and a short temper, or Taylor has blonde hair and not a short temper. So we can find that counterexample. So this would be a valid conjecture until you found that person or that observation or that example that disproves the conjecture. And we've been saying this all along, but the word for this is a counterexample. Mr. T. Mr. T coming at you. I don't know if you guys know who Mr. T is. We're going to get to him more later. So deductive reasoning goes the other way. You start with a big general rule, and then that will lead you to a specific conclusion. Let's look at some examples. Here's the general rule. So this time I give you the general rule and say the next number in the sequence is the sum of the previous 2. So you can use that general rule and you can fill out the sequence. Oh, then the next number must be 5. This is the only possible conclusion for the next number because the general rule has already been stated. Here's another example. Any ray that bisects an angle cuts the angle into 2 equal angles. The word bisect, bi meaning 2, like a bicycle has 2 wheels, and it cuts it right into 2 equal parts. So we would say this angle equals this angle. So the fact from that general rule or conjecture is that the ray is bisecting it, cutting it in half. So the specific conclusion is that they're equal. Again, this is the only possible conclusion. We would not be able to come up with a counterexample because the definition is true or the rule is true. So proofs by deduction in nature are way more powerful usually more useful when we're doing proofs by deduction because we know the general rule is true, so we can just follow it. That's me working out. All right, so again, let's look at that Sherlock Holmes example. If we look at it in reverse using deduction, we're saying this dog barks at every single person except its owner. So the fact that the dog did not bark at the murderer concludes the murderer is the owner of the dog. I know this is from a book, but it just goes to show how powerful deduction can be because we know it's true. I pity the fool who uses inductive or deductive reasoning carelessly. That's what he used to say. I pity the fool. Just be careful because when we're talking about reasoning and logic, it has a lot to do with the person who is interpreting the facts. So that can seem kind of funny when we're talking about mathematics because we always think math is just pure facts. And most of the time it is. And even in reasoning, it is, but it can just be a little more gray than usual. So let's try some. What type of reasoning is used? We're going to pick. A person knows that all the men in a certain room are bakers. We know this. It's given. Say, hey, everybody in this room is a baker. And all the bakers get up early to bake bread in the morning. And Jim is in this room. What can you conclude about Jim? Jim's a baker, right? He's a baker because they've already told us the general rule is all the bakers are in this room. They're saying all the people in the room are bakers. They didn't say most, a few, some, because sometimes we talk about this and say, well, Jim could have been, passing through. Jim could have been the manager on duty and checking on the bakers. And while that's true, we're using this rule that all of the people in that room are bakers. What comes next? What type of reasoning did you use? Oh, so this is deductive, right? Because we were given that big general rule about all the people in a room. Here, let's see if we can see what comes next. So triangle, triangle, star, triangle, triangle, star, triangle, triangle, star. They didn't tell us like the third shape is always a star. So we had to use the clues. We had to use the individual cases to see what would come next. So this is inductive. We can use that inductive to make that big statement and say every third shape is a star. So this leads us to conditional statements. Conditional statements should hopefully feel really familiar because you guys have done these in science since forever. My daughter's in first grade and she's doing them. Conditional statements have a hypothesis and a conclusion. So if something, then something. So this is always our hypothesis, the if part, and the then part is the conclusion. We do this all the time in science. We can turn any statement into a conditional statement. So here's our general statement. You may go to the movies after you clean your room. There's a few ways we can turn this into a conditional statement. So I don't want you to think there's just one right way. Here's one way. So if you clean your room, then you can go to the movies. That's one example. We could say, if you went to the movies, then you cleaned your room. So see, there's a few different ways we can write it. The most important piece is we have an if, we have a then, and it's based on the statement given to us. So let's try some. We're going to write these into conditional statements. So the first one says an acute angle measures less than 90. Let me get my pen. So we could say if an angle is acute, then it is less than 90 degrees. So you're really just turning it into that if-then statement. Sometimes you have to add some more words, like this example, all birds have feathers. We would say if an animal is a bird, then it has feathers. And we can talk about counterexamples again. Counterexamples are really powerful. Again, they're used in debate, they're used in science, they're used in math. And maybe there's an animal that exists that's a bird that does not have feathers. I don't know. I'd have to look that up. Ask Miss Mullins. She would know. How about this one? If today is Monday, then yesterday was Sunday. So hopefully you're seeing how to do this. We're just turning a statement into that if-then conditional form. And conditional means the truth is conditional. It's based on the hypothesis. So it's only going to be true if the hypothesis is true, right? You can write your own conditional statement about something we do in this class. So maybe, you know, if my classmate volunteers for a problem on the board, then I will support them. In the chat box. That's one I think of all the time. You guys are super supportive. So this is sort of a peek at some of the proofs we're going to be doing in our class that we're going to use reasoning and problem solving skills to get through. You're always given some information. Rules, definitions, statements, things like this, an equation. So you'll always be given something. And then usually, and it's not here, it will say prove. So it would probably say prove x equals -3. So sometimes you look at proofs and you're like, well, of course it is. You know, I can show you. I can plug -3 in and I can show you that it works. And sometimes you can do that, and that's sort of called a proof by example. But 9 times out of 10 in geometry, you're not going to be able to easily just show it. We're going to need to use definitions and theorems and postulates and examples to prove it officially. So these are called two-column proofs. You can see there's naturally two columns. We have a statements column and a reasons column. And whatever you write here on the left, you have to give a reason for. You have to give supporting details that shows the reader why this statement is true. So you always have a statement and a reason. And then you get down to the very end. And we're going to go through how to solve these proofs. There'll be some like drag and drop sort of opportunities where you're filling in the blanks to the statements and the reasons. I don't think on the assessments you ever have to do one completely on your own, but we will be doing some of those in class. So it's kind of like a puzzle. Following the inductive and deductive reasoning, there are two laws of logic. The first one is called the law of detachment. Sometimes you'll see this abbreviated LOD. Maybe I just do that. And here is what the law of detachment says. This is when we start to see P's and Q's and R's, sometimes S's. And I just want you guys to know that P and Q and R, they're just symbols. Like, it's not really a variable. You know, usually a letter is a variable. In this case, we're just using it as a symbol to make the shorthand quicker. And I'll show you an example. But the law of detachment says if P arrow Q. So let's talk about what this says. The way we read this is P implies Q. Another way is you can think of it as if P, then Q. So these all mean the same thing. Another way is we could say if, let me erase that D. If an angle is acute, then it's less than 90 degrees. So see, we're just letting, if an angle is acute, represent P, then it's less than 90 degrees, represents Q. So see, those letters are just representations or symbols for those parts of that conditional sentence. So it's like a shorthand. If that's true, and Q is true, whatever Q is, in this case, we're saying Q is less than 90 degrees, then we're going to use 3 little dots. P is true. These 3 little dots in math speak stand for therefore. You'll see them a lot at the end of proofs. And again, it's just a shorthand. It's funny. I wish I was like alive back in the day when mathematicians were sitting around the table. What should we write for therefore? And somebody chose 3 little dots. I wonder if there's more meaning behind that. Someone could Google that and take a peek. I might do that later. But you'll see 3 little dots at the end of a proof a lot. You'll also see hashtag at the end of a proof a lot. That means it's done, it's finished. We're going to use the 3 dots in our class mainly. It means therefore. So we're saying if P implies Q is true and Q is true, then P is also true. Oops, hold on. I got this reversed. Boop, boop. I was ahead of myself. There we go. If P implies Q is true and P is true, see, then Q is also true. And I know that's kind of funny seeing it in a bunch of letters, but if we look at it with some real sentences, it will make sense. Let's look at some. If I study for the test, so we're going to let this represent P, then I will pass. This represents Q. We're going to say, well, that's true, realistically. So I studied for the test, P. See how those match? Study for test, that's P. So therefore, Q is true. I passed. You can be happy. Now you could come up with counter examples, right? We talked about that. Maybe the person studied for the wrong test, studied the wrong material. That could be a counter example. But you can see this law of logic at play, the law of detachment. And some people remember the law of detachment as like this P is kind of detaching itself from here, kind of just a visual way to remember it. Because the second law, well, let's try one more LOD. So I'm a labeler, we're going to label it. Look, this one doesn't have any P's and Q's yet. So I'm going to let this be P, this is Q, and then let's make sure A is 45, A is 45. Yep, that's P. So we do have P, Q. Remember, if then can be written as P implies Q, then P. So we know by the law of detachment, Q must be true. So we would say angle A is acute. Is this an example of the law of detachment? So let's work through it. If I brush my teeth, let's call that P. Just always start with P. Then I will not get cavities. Q. My teeth are clean. Is that the same? This is not the same exact statement. It's not. It kind of means the same thing, but it's not the exact same. We can't label it P because it doesn't say brush my teeth. It doesn't even say brushed my teeth. It's not the same. So we would call this something else, like R. Therefore, I will not get cavities, Q. So is P implies Q, R, Q. See, I just pulled off the letters. P, Q, R, Q. Is this the law of detachment? Nope. This would have to be P, right? We don't know anything about R in this example. We don't know why the teeth are clean. Maybe they went to the dentist. Maybe they used mouthwash. Maybe they used their finger. I don't know. Maybe they got dentures. My grandma had dentures. Oh my gosh. I miss her. She used to like pop her teeth out for us and we thought it was so cool. Now, I mean, thinking back, it was a little gross, but it was cool. Let's look at that second law, the law of syllogism. So I'm going to write it out this way vertically. If P implies Q and Q implies R, then P implies R is true. So check this out. This really reminds me of the transitive property. You guys remember the transitive property from back in the day? Probably did it a few years ago. It says if A equals B and B equals C, then A equals C, right? These pieces match, so A must be the same. We could do some numbers. Like if A equals 2 and 2 equal, well, this is a bad example. Hold on. I always think of this, so this is a transitive property. Think of this like transit if you're driving. So if you drive to work and then you drive home, that trip back from home to work is going to be the same. So look, these Q's match. So that must mean P implies R. It's true. So let's look. If I pass the driving test, call that P, then I can get a car. Well, that's nice. Call that Q. If I get a car, see those match, so that's Q again, then I get a job. This is a totally new one, we'll call it R. So you're given these sentences, you label. Once you label, you have your letters to go ahead and pull out and see what kind of logic exists. Oh, look, these match. So that must mean P implies R is true. If I pass the driving test, then I can get a job. So again, I think it's really helpful to label. Pull it out here to the side if you have to. Some people don't have to. They can go straight from the labeling, and then you can see. So by the law of syllogism, there's our conclusion. Therefore, let's try again. So 2 angles are vertical. Call that P. Then the angles are congruent. Q. Oh, the angles are congruent. There's Q again. Then their measures are equal. We'll call that R. So P implies Q is that first sentence. Q implies R is the second. So therefore, we know by the law of syllogism, P must imply R. If 2 angles are vertical, then the measures are equal, which we know is true. There we go. Is this an example of syllogism? So we just start labeling. If I practice soccer, call that P, then I'll score in a game. Q. If I practice soccer, there's P again, then we will win. That's totally different, so we'll call it R. Therefore, they're giving us the conclusion. If I practice soccer, that's P, right? I'm just matching up. The practice soccer statements are all P. Then we will win. And there's R. Now it makes sense logically, but also we can show it is true by the law of syllogism. So the first sentence, P implies Q. P implies R. Oh, wait a minute. Writing out the law of syllogism like this makes us see more clearly. Therefore, P implies R. Do you guys see how this is not the law of syllogism now? So it's a really good idea to label and then also write it vertically so you can see those letters together. These do not match. This conclusion must match this premise in order for the law of syllogism to be true. So no, this is not LOS. So before we end today, I wanted to share with you guys some examples of advertising. And I crack up at these every year, and I tried to find some new ones. So these are some advertisements that I just found on a quick Google search. There are two different ones. The first one is Coca-Cola. And I'm wondering if we can come up with some conditional statements based on this advertisement. So all of the time in media, advertising, business, they're trying to get you to buy into what they're saying, whether it's to buy a product, to believe their statement, to believe their reasoning, to join their cause. I say they, whoever it is writing this ad or statement. And they people use all kinds of techniques. And logic is used in advertising all the time. And people don't even realize it. So the first one we could say, there's so many things we could say. I'd like for you guys to share one in the play posit. But, if you drink Coca-Cola, then you'll smile. I get that from the advertisement. They're all smiling. They're all drinking Coca-Cola. Let's see. What else? If you're young, then you'll drink Coca-Cola. That seems like some image they're proposing. Could you come up with a counter example? Maybe we could find a counter advertisement where there are some older people drinking Coca-Cola. So everything around business and advertising is always trying to get you to buy into what they're selling or what they're proposing. Check out this one. This is Beyonce, right? And she did this advertisement for, I think this is Crest. Oh, it's Colgate. It does say, this is interesting at the bottom, world's #1 dentist recommended toothbrush brand. And then there's a clause so tiny you can't even see it. Let me see if I can make it bigger to read it. Barely, it says based on surveys of representatives worldwide, samples of dentists carried out by P&G. Whenever you see statements like that, I encourage you, almost beg of you to ask questions. Who did they survey? Who are these dentists? How long have they been dentists? Are they getting paid to complete this survey? Are they getting free product to complete this survey? They don't have to share any of that with you guys on this advertisement. They just shared that clause and that was enough for them to make that world's #1 statement, but we don't know anything else about it. Now, of course, as a consumer, you're probably not going to solicit all that information before buying the toothpaste, but that's just a tiny example. As you guys are scrolling through social media or you're researching things, you definitely want to have that lens on to say, wait a minute, where did this data come from? How are they able to make these big, grand statements? What we're learning in geometry about the laws of logic. So very interesting. If you're Beyonce Knowles, then you use Colgate toothpaste. If you use Colgate toothpaste, you'll have a smile just like Beyonce. If you use Colgate toothpaste, then you'll be using the #1 dentist recommended brand. So see, we can make all these different conditional statements based on advertisements. And this is the new one I found for this year, and I can't stop laughing. What's the deal with human teeth and things that aren't supposed to have human teeth? Remember we saw a cat earlier, or a squirrel maybe? I can't deal. So this is a pistachio. And Philips Sonicare, you can see it in the bottom right. It's actually really small, which is interesting that they chose the item to be the smallest thing on the screen. It's probably to grab your attention. It's very eye-catching, this huge pistachio. The one on the left is very dirty. Well, quote unquote dirty. That's what a pistachio looks like. And then the one on the right is squeaky clean, shiny human teeth. So, conditional statement. If you use Philips Sonicare toothbrush, you will have clean teeth, right? That's what they're trying to get across. We could be silly. If you use Philips Sonicare toothbrush, you will turn into a pistachio. That's another conclusion off of this advertisement. I thought that was so silly. This does conclude our play posit for the week. I am so thrilled to see you guys in live class on Wednesday. We officially start the regular live class schedule, and you guys should see that on your Class Connect schedule and your plan for this week. I either see you have a few sections, so I either see you at 9 or 11, and then we have our office hours on the same day as well. So if you guys ever need any help, you can pop into those. Those are totally optional. And you can always send me requests prior. Say, I want to go over these specific questions, or you can just pop in and see what we're talking about. So I hope that you guys have a great week. Reach out if you need anything. Bye, everybody.